Internal combustion engines have a strict physical limit. Making more power traditionally requires a larger, heavier engine to pull in more oxygen. The workaround is forced induction, mechanically compressing the air before it ever reaches the cylinders. Packing dense, compressed air into the engine means you can inject proportionally more fuel. This yields massive horsepower gains from a surprisingly small engine block. Squeezing that air drives up internal temperatures and mechanical stress. It requires precise tuning and fuel management, so the engine doesn't simply blow itself apart. But the debate over forced induction focuses on a different problem: energy harvesting. The central question is where your compressor gets its power. This comparison matrix highlights the two main strategies. Turbochargers scavenge hot, expanding exhaust gases exiting your engine to spin a turbine. Because it recycles waste energy that would otherwise just exit the tailpipe, it is highly fuel efficient. Building up enough exhaust pressure takes time, which creates a slight delay in power delivery. Superchargers connect mechanically directly to the engine's crankshaft using a belt. That direct physical link means power delivery is instantaneous and highly predictable. But spinning that compressor takes horsepower. This creates parasitic loss, actively draining your fuel economy. Every system demands a compromise. You choose to sacrifice either response or fuel efficiency. This graph maps a turbo's power curve. At low RPMs, exhaust volume can't spin the turbine, creating a flat boost threshold. Below it, your engine is naturally aspirated. Once crossed, you press the pedal and wait. That gap before feeling acceleration is turbo lag. Bolting on a larger turbo pushes incredible volumes of air from maximum peak horsepower, but it requires even more exhaust to spool up, making that lag significantly worse. Thermally, turbos are mounted directly into the searing hot exhaust manifold. This positioning allows them to capture existing heat energy efficiently. However, extreme underhood temperatures require complex intercooling systems and heavy heat shields. Shut the engine down while it's too hot, and the oil inside the turbo bearings can bake into solid carbon. Turbos are the ultimate efficiency tool, but they demand precise thermal management and a little patience from your right foot. This decision tree maps out supercharger styles. If we follow the branch to positive displacement units, we see a steep, highly linear power curve. These pump a fixed volume of air per revolution, delivering peak boost almost immediately off idle. The trade-off is that power eventually plateaus at the top of the RPM range, making them less efficient at high vehicle speeds. Looking at these technical diagrams, you can see the differences between a standard roots blower and the upgraded twin-screw design. A twin screw physically squeezes and compresses the air internally between the rotors before it ever reaches the intake manifold. These bar charts quantify the difference. The twin screw carries a higher initial component cost, but it drastically lowers discharge temperatures and reduces parasitic power loss. Physically, a positive displacement supercharger usually bolts directly to the top of the engine block. Because you avoid cutting into the exhaust system, aftermarket installation is relatively straightforward. That top-mount setup often requires cutting the hood or buying a specialized replacement for clearance, like you see on this Hellcat. It also completely abandons the fuel efficiency benefits of a turbo. Superchargers provide unapologetic, instant torque and simplified plumbing, but they actively tax your engine's own power to do so. Engineers have built systems to eliminate the compromise entirely, using twin charging and 48-volt electric turbos. This flowchart tracks a series twin charger setup. Air routes through a supercharger, into a turbo, then the engine. Once the engine hits mid-RPM and the turbo spools, a bypass valve opens, shutting off the supercharger and letting the turbo take over. This mechanical combination was pioneered on cars like the Lancia Delta S4. Today, manufacturers are achieving the same result using electricity. Modern electric superchargers, like the one inside this Mercedes-AMG, use a 48-volt electric motor to spin the compressor instantly, perfectly filling the low-end lag gap. These systems introduce extreme complexity and exorbitant repair costs. Right now, they are mostly locked to high-end, factory-built luxury cars. Hybrid systems combine the traits of high RPM efficiency and immediate low-end response, but they extract their toll in massive engineering and maintenance costs. This quadrant chart maps the hardware to the driver. We have efficiency versus raw power on the vertical axis, and OEM versus aftermarket builder on the horizontal. If you are an OEM buyer prioritizing fuel economy and passing power, the modern turbocharger is your definitive choice, provided you accept a momentary hesitation from a dead stop. If you are an aftermarket builder who needs towing torque, off-road crawling capability, or stoplight-to-stoplight muscle, the Supercharger gives you the necessary instant linear torque curve, but you actively choose to sacrifice your gas mileage. For the buyer who needs a power band with both immediate low-end torque and high RPM flow, you're looking at hybrid solutions. You get perfect power delivery, provided you possess a massive initial budget and accept highly specialized lifetime maintenance. The best forced induction system doesn't exist in a vacuum. The right choice depends entirely on whether you prioritize your wallet at the pump, your launch at the track, or your mechanic's labor bill.